We turn now to density of states engineering for optical structures, analogous to the density of states engineering we talked about earlier for electronic structures. Just to remind you, in 3 dimensions, if we plot the number of states per unit energy, the density of states against energy, we have something that looks like E to the 1/2 in 3 dimensions. In 2 dimensions, the same plot now looks like a constant. In 1 dimension, i.e. a wire, the density of states looks like e to the -1/2. And of course, in the case of 0 dimensions, the density of states looks like a delta function. So I show you here the same kind of plot of density of states against energy, but plotted here for a laser. The laser medium will have some profile of gain versus energy, and this will be the intrinsic gain versus energy will be multiplied by the density of available states to give the actual gain versus energy profile. For a laser, the important thing is that the intrinsic gain, i.e. if one puts so many photons in, how many photons come out, the intrinsic gain must be greater than the losses of the resonant cavity. So a typical laser will have some material that has an intrinsic gain stuck between partially silvered mirrors, and these then result in a multiplication of the amplification as the light bounces by a large number of times before being emitted. So one requires then that the overall effective gain be greater than the losses in this resonant cavity. If this same density of states now is, because of the number of amplifying atoms per unit volume, is squeezed into 2 dimensions, you can see that the gain now is squeezed into a narrow range of frequency compared with 3 dimensions. In the quantum wire, the range of frequency is narrowed even further, leading to more states lying above the cavity loss line. And finally, with quantum dots, the density of states is squeezed even further into what is almost a delta function, and so therefore much more gain is available from the medium. The picture on the left shows a semiconductor heterostructure in which the laser medium is a series of quantum dots. The device is further optimized, in addition to the increased density of states now for emission of radiation given a stimulus, by engineering the band structure by the appropriate layering of this device, so that in the region with the quantum dots, illustrated like this now, here is the valence band and here is the conduction band. In the region with the quantum dots in it, the energy states for holes are made lower. Remember, going upwards in energy for a hole means lower in energy, and the energy states for electrons are made lower, so that electrons from the conduction band tend to fall into this region here of lower energy, and holes from the valence band tend to fall into this region here of lower energy, so that excitons then can stimulate optical emission from these quantum dots, which themselves have energy focused in the region of resonance of the surrounding cavity. Another type of density of states engineering comes in photonic crystals. The basis of photonic crystals is just Bragg reflection, and it's illustrated here for this beautiful piece of opal in which these lovely colors come from the selective reflection of particular wavelengths of light at certain angles in the crystal where the orientation of periodic material is just right to reflect those wavelengths. This here is an artificial opalescent material made actually of polystyrene spheres, as illustrated over here in this electron microscope image. And these also are periodic and reflect optical wavelengths, much like an opal, but as I say, an artificial structure made from polystyrene spheres. The problem with materials like this is these Bragg reflections still occur in certain directions. They do not have a genuine optical band gap. Why might one want an optical band gap? Well, if one has a source of energy, thermal energy for example, and plots the emission intensity versus wavelength, one gets this classic in equilibrium black body spectrum that comes around from Planck's law. Planck's law states that the emitted intensity is proportional to the cube of the frequency of the light, so the wavelength is the speed of light divided by the frequency, times the Bose-Einstein factor, and from this the black body radiation spectrum can be predicted. If one were to have an object emitting light not in contact with the vacuum, which is how this law was derived, but instead in contact with a material that has the transmission of energy forbidden in certain regions, then the emission of light from this hot object would change dramatically. This led to the proposal for the manufacturing of photonic crystals. This shows a calculation from the original paper. Here is the frequency versus propagation direction in the crystal. And what you see is there is a genuine band gap shown by this shaded area here, in which light will not propagate inside this photonic crystal. How is this done? Well, the right-hand image is a scanning electron micrograph of a photonic crystal structure. And so let me tell you how this works. If you take a periodic array of point atoms and consider the diffraction of light by this structure, then there will be allowed reflections at some angle, theta b, a Bragg angle. However, remember also that each of these atoms, which we'll no longer consider to be points but things of finite size, has itself a diffraction pattern, which now as a function of the angle of the scattered light might have an intensity distribution that looks something like this. So light diffracted at these angles here would correspond to a minimum in this diffraction pattern. This scattering from a point particle here, or a finite-sized atom, is called the structure factor of the crystal. And so if it is arranged that the structure factor of the crystal is exactly zero along the Bragg angles, then Bragg reflection is completely forbidden in the crystal. This funny-looking structure here, looking as though it consists of stacked rods, in fact has a structure factor chosen so that the allowed Bragg reflections corresponding to this spacing here between the so-called atoms of this crystal, of course they're much bigger than atoms, exactly is cancelled out by the structure factor of the individual units in the periodic crystal. The result is that in this optical band gap, radiation cannot propagate. An experiment is being carried out in which a structure like this has been made of refractory metal, heated up to a temperature that should result, according to the Planck radiation law, for radiation, let's say, in the red. And in fact, the photonic material radiates in the visible because of the squeezing of the density of states in what would have been the vacuum into a region with a photonic band gap.